record.
So hello to everybody. This week's seminar for the series North Atlantic Non-Commutative Geometry Seminar is given by PIOTR HAJAC, and the title is The K-Theory Type of Quantum CW Complexes. So PIOTR, please, you can begin.
Thank you so much. I apologize again about the slight delay, but it's not so easy to be simultaneously a recording host and a speaker. As you can see, this is based on joint work with Francesco, who just kindly introduced me, Tomek Maszczyk, who is somewhere there, hidden and muted, Albert Schuh, who maybe will turn up during the talk. Yes, hello, Albert, he is here from Kansas, and Bartek Zieliński, who I hope also will come. This is based on our joint work. This is a very, very long paper. It has about 60 pages. Francesco gave already a sneak preview about this topic at the other non-commutative geometry seminar. I don't remember when, sometime in January, I suppose. But we made a lot of progress since then. So even if you attended Francesco's talk at the other seminar, this is going to be quite a different story. We've done much more. In fact, let me make a disclaimer from the start. I cannot cover the whole story in just one talk. So you can think about my talk as part one of a two-part talk, with the second part being given by Tomek Maszczyk on 12th of January next year, okay? Because there are some very exciting new aspects of this story, which were unraveled only very recently, and there's no way to squeeze everything into one talk. Okay, so now let me begin with some motivation, and let me apologize again. I'm not so fluent with using drawboard PDF, but I need to write quite a bit during my talk. So for me, it's really quite necessary to have this drawboard PDF and this facility of being able to write. Okay, and now what? Now it's frozen. It's the usual problem with Zoom. It's frozen. I cannot move it. I cannot change the page. Oh, I can do it now. Okay. But this is too much. Oh, now it works. Okay, excellent. So let me begin by the motivation. Don't worry, I will explain everything in the course of my talk. But I don't want to start by dry definitions and formalities in terms of categories. I would like to first give you a motivation of why at all we're excited about it. But since I am already so excited about it, let me grab a watch so that I don't go over time too much. All right, now the time is under control. So already a long time ago, a bunch of people, first, I think it was Francesco, Francesca, Mariusz Tobolski, and myself, we proved a certain theorem about trimmable graphs, hysteralgebras. And then we proved it in the category of U1 hysteralgebras, and we had a certain pullback structure for graph hysteralgebras. And then, because everything was equivalent, we could go to fixed point hyster subalgebras. And these subalgebras happen to be exactly the hysteralgebras in the diagram that you can see in front of you. These were now I'm having here the hysteralgebras of the Waxman-Sobelman quantum complex projective spaces, of the Waxman-Sobelman quantum odd spheres, and Hong-Szymański balls B2 and Q. And this was a nice consequence of our theorem about trimmable graphs. But then in another paper joined with Alex Kirvasitu and Mariusz Tobolski, we had a completely new, purely graph hysteralgebraic approach to pullback theorems. We're looking for most general pullback theorems in the realm of graph hysteralgebras. And then we proved such a theorem. As a very special case, a motivating case, we had this pullback structure, which is right here in front of you. Okay, so although the title of this slide is going beyond the naive doesn't mean trivial or easy. Actually, this is a non-trivial theorem to prove that we have this pullback structure. And then, of course, you can ask, why on earth do you bother about having such a pullback structure? You definitely cannot claim that you need this for computing by K-theory. because computing K-theory in this case is a triviality. You can immediately get the K groups. However, what is more interesting is to determine generators of these K0 groups. And then this pullback diagram and the Meyer-Vittorius external exact sequence in K-theory are very handy with the Milnor connecting homomorphism and so on and so forth. We have this picture which is very geometric and closer to what you have in the classical setting for Q1. So we had some, motivation to study such a pullback diagram, and we proved that it was a pullback diagram. We have two independent proofs. And now we can be naive and say, all right, but this is precisely what classical gives a CW complex structure. So why not to use it to define, in general, finite quantum CW complex structure and claim it as our example? Well, that's exactly what we're going to do, because indeed these pullback diagrams inductively yields the so-called filtration by Skeleta. So this is this line. You simply have such star homomorphisms going from higher CPN C-star algebra to lower dimensional CPN C-star algebra for any n, for any dimension. So you have such a filtration. And this renders with Waxman-Soberman quantum complex projective space a finite quantum CW complex defined in a naive setting. But that's not the end. You realize that if you go beyond this deformation, like another deformation quantization of complex projective spaces, one which we call multi-pullback. So that's something that we found with Bartek, Zieliński, and Atabey-Kaigun ages ago. And then you want to study the potential CW complex structure, non-quantum CW complex structure for these C-star algebras. Well, you bump into a problem, because the fundamental map which we enjoy here, namely this star homomorphism, which is very easy to write down, in fact, this refuses to exist. I don't want to say that it doesn't exist because I don't have a no-go theorem, but any natural attempt to create such a star homomorphism failed. Okay, so this is why I say that this one refuses to exist. Yet the K-theory structure is as deep and as rich as we have it for Waxman-Soberman deformation quantization. So we somehow wanted to fix it. Anyway, we had to fix it because otherwise we wouldn't be able to prove certain things about these quantum projective spaces that we wanted to prove. So we wanted to fix it anyway. And this led us to a notion of a weak quantum CW complex. And this, or I have a question in chat, let me see if I can answer. How does one define this quantization? Oh, it will come, Alex, it will come. This is, hello also, yes. This will come, Alex. It's just my motivation page. I didn't want to start my talk by defining for you zillions of categories, okay? I'm going to do it right now, but now I hope that you are properly motivated and you see why I'm doing this. Okay, so it will all come. And in fact, let's see if I can change page. Again, this got stuck. Okay, now I guess it's unstuck. Yes. Okay, so now we are speaking concrete things. In order to overcome this difficulty, we had to define a certain version of a Waldhausen category, but I don't assume that you know what the Waldhausen category is, so let me recall. So an unpointed Waldhausen category is a category with an initial object denoted here by the empty set, a terminal object star, and with two distinguished classes of morphisms. Mind you, these classes intersect; they are not disjoint. One of class is called COF. This is the class of morphisms that we call cofibrations. Another one is called WEC. This is the class of what we call weak equivalences. So we have these two classes of morphisms. Some are called the first morphisms in the first class are called cofibrations. Morphisms in the second class are called weak equivalences. And they have to satisfy some axioms. Okay, so first for cofibrations, so we say that all isomorphisms are cofibrations, and then when you take the unique morphism which comes from our initial object to any other object X, it is a cofibration. then we want to demand that cofibrations are closed under composition. By the way, my dear co-authors, this axiom was missing in our paper. I checked it on in the literature, and we need it actually. We need it in our proofs, and it is a part of a definition of Waldhausen category. So I added it, but it's missing in our paper. Now we have C3. Well, that's something I'm going to explain. This is how a cofibration is compatible with push-outs. So formally speaking, if I have a morphism from X to Y, which is a cofibration, and then I have a morphism from X to X theta, which is just any morphism, then the induced morphism, right? Because when I have a morphism from X to Y and from X to X tilde, then I can take push out of these two morphisms. So in particular, I'll have a morphism going from and I think I didn't. No, it's okay. Sorry, I'll have a morphism going from X tilde to the push out object. Okay, and this should be a cofibration again. I will explain it in the concrete case of having the Waldhausen category of compact quantum spaces.
May I have a question?
Sure.
So we are assuming that the category contains push-outs, yes?
Yes, yes, yes.
Okay.
Definitely. Now, when we go to axioms for weak equivalences, again, all isomorphisms are weak equivalences, so isomorphisms are both cofibrations and weak equivalences. Then we want the weak equivalences to be closed under composition, and we want weak equivalences to be closed under gluing. And it's closed under gluing is in a very specific sense. I will try to write it for you. This was too much to type up. There are lots of diagrams, and it will take me forever to type it up. I'll try now to write it for you, but I have to make sure that I'm writing the right thing. So I'm finding this axiom in our paper. Well, this is about what happens when you put together two push-ups. Okay, but I want to make it precisely, so I need to find the right thing in our paper. Okay, I'm almost there. Yes. So given any commuted diagram of the forms, any diagram which looks like this. Well, I have X and weak equivalence going to X tilde. I have Z and the weak equivalence going to Z tilde. And I have Y and the weak equivalence going to Y tilde. And now what I have? I have vertical arrows are weak equivalences and right horizontal maps are cofibrations. So here I have cofibrations. Cofibrations. And do I have any assumptions here? No, I don't think so. Vertical arrows are equivalences and the right horizontal maps are cofibrations. Yes. So then, because this is a commutative diagram, by the very universal property of a push-out, we have induced map. So this goes from the push out of Z with Y over X into the tilde push out. So the push out of Z tilde over X tilde with Y tilde. So this induced map is a weak equivalence. Okay, so that's the meaning of his W3 axiom, which we baptized as gluing of weak equivalences. Okay, and yeah, and I guess that's this is what we are doing. We have these vertical arrows are weak equivalences, and we are gluing them. We are, and this means that the induced map is again a weak equivalence. Okay, I still have a question in here. Okay. Oh, it's just absolutely all right. Okay. Next. So this is what is Waldhausen. This is not our doing, and from what I remember, Waldhausen did it in order to study algebraic K-theory. So this was his motivation. And now, of course, this is again frozen, so I have to do some magic. It gets unfrozen. Okay, and now this is our baby, and we call it. What
was Waldhausen's category?
I just here it is. Oh, sorry. Here it is. Basically, you have.
What was his example? What was the category he was interested in?
Oh, I cannot speak on behalf of Waldhausen.
Yes.
This I cannot answer. I emailed him the Zoom link to this talk, but I don't know what exactly he wanted for himself. We are going to work with a Waldhausen category of compact quantum spaces, which means unital sister algebras, and we'll have some English.
He was interested in questions involving diffeomorphisms of manifolds.
Okay.
And and cobordisms of manifolds, and so I mean he was interested in very interesting questions.
Mm-hmm.
And he made an absolutely amazing observation, which is this idea he has of the Waldhausen category.
Mm-hmm.
I mean, in my opinion, this was a great idea.
I couldn't agree more.
Yeah, a Waldhausen category has K-theory, and this is somehow the most general setting and is somehow the correct setting
mm-hmm.
for K-theory. But this was an absolutely great thing that Waldhausen did. Is he watching?
Well, I mean, I sent him an email, but he's retired, so.
Yeah, he's retired, but so what? A lot of people are retired.
Yeah, exactly. That's why I sent him an email with my title and abstract.
What's his first name? I forgot his first name.
Oh my goodness, it begins with an F, but Friedrich? It's not Friedrich.
Freihausen. All right. Okay. All right.
Yeah.
All right. Well.
Okay.
In my opinion, this was an absolutely great thing. He pinpointed a really important property. Now, mm-hmm. But you don't know the example he had in mind. I think it was, okay. I mean, he had a very important and basic example in mind when he made these axioms.
I can guess. We needed very little tweaking to adjust it into our category of unital sister algebras. Very little. Yeah.
Well, that's part of the miracle of all this.
I agree. Right. Because look, the only thing that we do, we are adding one more axiom, just one more axiom. We call it CW axiom, but this is not for CW complex, although we need it for CW complexes. This is CW because it's cofibration weakening. Okay, so we call an unpointed Waldhausen category a CW Waldhausen category, which means cofibration weakening Waldhausen category. If for every push-out diagram, of course, in this category, with J being a cofibration and H being a weak equivalence, H is a weak equivalence if and only if G is a weak equivalence. Okay, so that's the axiom that we are throwing in, which was not in the original definition of Waldhausen.
When you talk about a cofibration,
mm-hmm.
I think the classical example of that is the inclusion of a closed subset, right?
Yes, exactly. Yes. For us, this will be subjective unital.
Well, it has to have some properties. I mean, it can't be completely crazy, but the classical example, I think, is inclusion of a closed subset in a topological space.
Yeah, I agree. Yeah, definitely so. For us, this is surjections on C-star algebras.
Oh, I see. For you, this will be a surjection.
Yeah.
Oh, so your cofibrations will be surjections of C-star algebras.
Correct.
Now, one thing about this, I mean, one of Waldhausen's main points, because this was very important in what he was interested in, which had to do with geomorphisms of manifolds and cobordisms of manifolds. When the manifolds are not simply connected, for example. I mean, all right.
Oh, I just got the answer to your question. His first name is Friedhelm.
Oh, Friedhelm. Okay, great. Yeah. Okay.
Yeah. So this question I can answer. I cannot answer the question what he had in mind.
When you have a category with all these axioms, one of the things Waldhausen did was he constructed the K theory for that category. So if you are going to take the category of C-star algebras, that will, and then you will show what are the weak equivalences and what are the cofibrations, and that it satisfies Waldhausen's axioms plus this extra axiom. So you might ask, what is the K theory for that? I don't think it will be what we usually call K theory of C-star algebras. It will be some kind of algebraic K theory.
Well, that's above my pay grade for the time being.
Well, not necessarily. It might not be above your pay grade. But I don't think it's above my pay grade. I would like to know what in order to recover what we usually call C-star algebra K theory, you have to take into account, in some sense, the fact that the morphisms between two C-star algebras are topologized. There's a topology. And it might be, I'm not sure whether Waldhausen's axioms do that or not. Okay.
I'm sorry. I cannot help you. Okay, but let's continue. Oops, again, it froze. So I have to do some magic. Yeah, and now it works. So you see, now what we do, the next step, I think that this is called making the homotopy category. What we do, we formally invert all weak equivalences, and call the morphisms in the class of the form inverted weak equivalence composed with cofibration. We call such a morphism weak cofibration. So this is the way we add morphisms into our category. Okay, and this is no longer called the Waldhausen category. This is, I think, Tomek, correct me if I'm wrong, this is the homotopy category of this Waldhausen category. But I don't want to multiply here the linguistics. So what is really important is that we have this axiom and that we have this weak cofibration. This is absolutely crucial. This is why I have it in red, because we cannot make sense out of a CW complex structure for the multiple but complex quantum projective spaces without this concept of weak cofibration. So this is absolutely pivotal for us. Okay, so this is done. And now, well, if I am to have a category, I better be able to compose. So I want to show you that I can compose weak cofibrations, and better still, that the composition of weak cofibrations is again a weak cofibration. And look how these weak cofibrations are defined. I think that such triangles are called cospans. And you have a roof-like structure. You have a weak cofibration J going from Y to Z tilde. And you have a weak equivalence going from Z to Z tilde. So sort of, and this is what happens to us in real life when working with sister algebras. We have maps going the wrong way. But they are equivalences in some sense, and it makes sense to invert them. So here what we are saying is, all right, that our morphism, our weak cofibration is an arrow going from Y to Z, which we can think of as the composition of H inverse, this formally inverted weak equivalence with J. Okay, and now how do I compose such two things? Well, here I have a recipe for the composition. Basically, here's a bit awkward because you write it in the other order that you would compose arrows, right? Whenever you write, I don't know, F composed with G, and when you depict this as arrows, then it means that you first have a G. Oops, I touched something in it. Yeah, so it goes in the other way, right? You first have G, but you then have F. So circle somehow inverted. If we were writing in Arabic from right to left, it would have been easier. Anyway, yeah, did I do it correctly? Yes, of course, yes. Now let me erase it because I don't need it. So where is this eraser? Oh yes, here it is. So why can't I erase these two arrows? Anyway, let's not bother about this. But now if you think about this left roof as being on the right-hand side, then you can see that they have a common object, Y, and you can think about composing them. In fact, this is what you have on this picture. Oops, but now I need to switch to a pen. That's what you have on this picture. So you put these two roofs next to each other, and now you need to have for X and Z, you need to have some Z tilde and a map from X to Z tilde, and a map, sorry, Z double tilde, and a map from Z to Z double tilde, which satisfies all the axioms. Okay, so for starters, when we have G and J, all right, so I look at this part of the diagram. Well, we can take the push out. The push out is well defined, it exists. So I take the push out, and all these maps are well defined in my category. They are uniquely defined.
At this point,
yes,
what you have on the screen here,
mm-hmm.
very, very close to KK theory, what you are talking about. This is very close to the Kasparov KK theory.
I will explain our intimate relationship with KK theory once we get to sister algebras.
Great. Okay.
Right now, this is some abstract mumbo jumbo in category theory, but I think about it all the time in terms of sister algebras and compact quantum space. Again,
well, this is very close to KK theory. This is what KK theory is, in fact, what you have on the screen here.
And Alex Frey says that it's even K theory. In fact, the original construction. I'm just reading the chat.
Not K theory, like
E theory.
Like who did the E theory?
Nigel Hickson.
Yeah, like that was like the first, the original construction of E theory.
Okay. Great.
The original paper, like before the joint with Con.
Mm-hmm. Okay. Okay, let me go on.
Can I just have one comment or perhaps question?
Go ahead, Bartek, of course.
So this composition of cospans, if you would invert it, you would have a composition of spans, and the composition of spans is just a composition of binary relations, and in fact, if one of the arrows would be an isomorphism, it would be more or less like composition of functions, because then the relations would be functions or partial functions or something like that. So I was thinking if those things could be understood as some kind of functions on function spaces.
I don't know.
Because this somehow, so it's like dual of functions or something like that, those cospans.
Yeah, but I definitely cannot answer this question, but I'm happy that it rings a bell in yet another church. But but let me carry on. I honestly cannot comment this, Bartek. So, so let me carry on and reach sister algebras. Okay, so now let's see that what do you want to do? Of course, once we complete these two morphisms G and J into the push-out diagram, then we have uniquely determined these maps J tilde and H tilde. So now, of course, we can compose. We can compose I with J tilde. We can compose H with H tilde, and declare them to be our desired morphisms from X to Z double tilde and from Z to Z double tilde. Well, excellent, very good. But we still have to check that this makes sense, because if you are to have a map from X to Z, we must have that H tilde H is a weak equivalence, because otherwise we cannot invert it. Okay. So first we have to verify that H tilde H is a weak equivalence, but you see CW guarantees that H tilde is a weak equivalence, right? Because G by assumption is a weak equivalence. So the CW axiom guarantees that so is H tilde. Then we have this W2 axiom, which guarantees that composition of weak equivalences is a weak equivalence, and H by assumption is a weak equivalence. So therefore the H tilde H is a weak equivalence, and we can invert it. So the composition makes sense. The composition makes sense by these two axioms, CW and W2. However, I still want to know whether it's a weak cofibration. And now to prove it is a weak cofibration, I have to argue that J tilde composed with I is a weak cofibration. Now, I is a weak cofibration by assumption, but now it follows from this axiom C3, this axiom I'm going to explain in terms of pullbacks of sister algebras, that if J is a cofibration, then so is J tilde. So this follows from axiom C3. And then we have also the axiom C2, which says that the composition of cofibrations is a cofibration. Okay. So now we are home and dry, because we know that J tilde composed with I is a cofibration, and we know that H tilde composed with H is a weak equivalence. So indeed, as a result of this composition, we have a weak cofibration from X to Z. Okay. Any questions here? All right, so let's continue. Again, I have to freeze and unfreeze. Now we're going to be concrete, and I'm going to define for you our CW Wellhausen category. So we take as our category the opposite of the category of unital sister algebra. So this is for us the category of compact quantum spaces. So objects are obvious. Objects are unital sister algebras. There is no question here. But now we really want to figure out what our morphisms are. That's the name of the deal. And this is why we have to bother with all this CW Wellhausen story. Okay, so now we take unital star homomorphisms as opposite morphisms. This is to begin with. We take the zero sister algebra as an initial object. We take the field of complex numbers as a terminal object, because this is what we need to have in an unpointed Wellhausen category. And now, as I was mentioning, I take surjective unital star homomorphisms as cofibrations. Okay, so if you want, when you dualize and you talk about arrows between compact quantum spaces, these will be injections. And now this is the most important part. So let me try to highlight it. Let's see if I can do it.
So sorry, this initial object is as an object in the category of the compact quantum spaces, yes?
Yes.
Seen as a sister algebra, but meant in this category. Yes. Usually is the other way around, yes?
Well, I mean, zero sister algebra, as George Eliot would put it, is the sister algebra of all continuous complex valued functions on the empty set.
Yes, and empty set is an initial object in sets. Yes.
Voila. Exactly.
So is initial in the opposite category? I think this was the question. Is final in the category of sister algebra?
Yes, exactly. That's what
but I said it's very clearly. I mean, opposite morphisms. So star homomorphisms are not my morphisms. Opposite morphisms.
I see.
Yeah, because I take the opposite of the category of unital sister algebra. Okay. So
yes,
I think I made it clear. Yeah. And now here is the punchline. So I take unital star homomorphisms inducing isomorphism on K theory as weak equivalences. All right. So any homomorphism between sister algebras, as long as it induces an isomorphism on K-theory, this is what I call a weak equivalence. Okay.
If we have two of your unital C-star algebras, let's say A and B, and we have what you are talking about, a unital star homomorphism from A to B, which induces an isomorphism on K-theory. Your category, does that go from A to B or from B to A?
Well, let me write it down.
It goes from B to A in what you are talking about.
Yeah, I'll write it down. Just give me a second. I just have to pick my pen again. Where is it?
Because you are taking the opposite.
Yeah.
All right. Okay. Fine.
Yeah. So
if we have in the usual sense, the usual sense we usually are discussing, we have a unital star homomorphism from A to B, which induces an isomorphism on K-theory. In your sense, that is a weak equivalence from B to A.
Exactly, yes. Well, from underlying quantum space. So that's a bit awkward. But you know what? It really helped us with organizing the math. So I was very resistant to dropping sister algebras and writing dual objects. But when you are dealing with this CW-Wellhausen category, this is actually quite useful. It's more straightforward. But now I think about A and B, of course. I think about them as some C of X, where X is some quantum space, and C of Y, where Y is some quantum space. So in fact, I have some map, I don't know, let me call it F tilde from Y to X. So this is my morphism. So I say that the morphism from Y to X is a weak equivalence if the induced map for the K-theory is an isomorphism. And by induced, I mean I go to sister algebras, I take my star homomorphism, I have my covariant functor of K-theory, and it gives me a map between abelian groups. And if this map happens to be an isomorphism, I say that this is a weak equivalence.
But when we have a map, one of your unital maps from A to B, which induces an isomorphism in K-theory, the basic examples of this are somehow are that you stabilize A and B, that is, you tensor with compact operators.
But then it's no longer unital.
Aha.
Yes.
All right. So we tensor with n by n matrices. I mean, the basic example of this, it seems to me, is a Moridi equivalence, except maybe you have to tensor with n by n matrices, something like that.
Well, it's I can tell you what is a typical example for us.
Yeah, what's a typical example?
Yeah, this is how it started. How about the unital map from complex numbers to the Teplitz algebra?
This gives an isomorphism in K-theory.
Exactly. You can put here Jiang-Shu sister algebra if you want.
Because K-theory is trivial.
Yes. Well, I mean, trivial in the sense that it's generated by 1 in the algebra. It's not 0, right?
It's non-zero. You're talking about unital C-star algebras.
Yes, exactly. Yes.
Like for von Neumann algebra, something like that, it could be trivial. It could be 0. But it's not 0 here.
Yeah.
But it's trivial.
Yeah. Yes. But you know, it's no longer trivial once you arrange it into more complicated situations. This is your building block. This is your atom, right? This is just.
You take this example and you tensor with n by n matrices for some big n.
Well, okay. So let me make some space.
What does that become a Moridi equivalence?
Somebody was saying something. I can try to see.
Okay, all right, okay. All right,
I'm trying to erase to write your question.
So this is an interesting example of a weak equivalence. Okay. All
I
right.
showed you our atom, and out of this atom will build life, molecules, you know, DNA and so on.
So
But Piotr, you should mention published sphere and mirror quantum sphere that are not Morita equivalent, but they are
Yes, wonderful, Francesco. Thank you so much. It's really wonderful to give a talk with 4 co-authors in the audience. This is fantastic.
Okay, good.
Yeah.
Okay, what's the example? Wait, let's get the example.
I'll write it down. I'll write it down.
Oh, okay, great, good.
So you see, you have a published generic published quantum sphere, or the equator one if you want. Well, that's a certain sister algebra, and but this is not a graph sister algebra, and we have a proof done by Wojtek Szymański that this is well, how to write it down, is not Morita equivalent. You just study positive cone in the K field. To what we call the mirror quantum sphere. And no, sorry, here instead of a, here instead of infinity, let me write a minus.
So I think our notation was infinity plus and upstairs and infinity with minus upstairs.
Yeah, whatever. Yeah. Okay. But anyway, these are 2 different sister algebras that not only are non-isomorphic, but they are not Morita equivalent. Okay, and it's a nice application of K theory to prove this lack of Morita equivalence, right? But not just K groups. You have to use, of course, K groups are the same, but they are K equivalent. And how can you prove it? Well, you can prove it because of the following phenomenon. Now we take the minimal unitization of compact operators, which is the standard published quantum sphere, and lo and behold, here you can construct star homomorphisms to both of these sister algebras. And both of these both of these homomorphisms, they are by no means isomorphisms, but both of these homomorphisms induce isomorphisms on K theory. So the generic or the equatorial published quantum sphere is equivalent to the standard, and the standard is equivalent to the mirror quantum sphere. Therefore, the mirror quantum sphere and the generic published quantum sphere are K equivalent, even though they are not even Morita equivalent. So surely this is a broader concept.
There might be examples using the Voronovich quantum groups.
Well, 2 of these sister algebras come from SUQ2, of course.
Yeah. Okay. Good. Okay.
No, it definitely comes from quantum groups.
No, but the Voronovich quantum groups, it's a deformation of usual Lie groups. Mm-hmm. But correct me if I am wrong, but I think that the K theory of the reduced sister algebra stays the same.
Aha, very good point. But this is not enough. It's not enough for us that the K theory is the same. We must have that this isomorphism is induced by honest to God star homomorphism.
Yeah, very good. Is that
That's
the case with the Voronovich examples?
Well, I mean, but what is the other thing? When we have to give me a pair. So one is SUQ2, and what's the other thing? Well, actually, yes. The other one is our HAJAC quantum sphere. Remember the paper, Paul, we wrote in Mittag-Leffler? That's exactly, yes. We have some funny HAJAC quantum sphere, and this is K equivalent. This is or if you want, this is equivalent in the sense, weakly equivalence in the sense I just defined to the Voronovich SUQ2 sister algebra. Yes, that's an example. Mm-hmm.
Okay, thank you.
Yeah. But it's not so immediate. I mean, it's not like you can immediately write a star homomorphism. You see it from the pullback structure. Okay, so now, wow, I'm doing so badly in time. This is my fourth slide out of 15. Looks hopeless. So let me speed up a little bit. Let me just mention that all the first axioms, okay, we have 7 axioms to check, and 5 of them are trivially satisfied. But I promised to you to explain one of them. I think it was C3, okay? And here push-outs of these quantum spaces, compact quantum spaces, are simply pullbacks of sister algebras. And when you study sister algebras, you have the following phenomenon. You take, I have to choose a pen. It's not so easy to manipulate this drawboard PDF. I'm not used to it yet. Okay. So imagine that I have a pullback of sister algebras. But I have a one surjective pullback. Say this map from A to C is surjective. So here I have my pullback sister algebra, and I have a map here, and I have a map there. And guess what? You immediately can conclude that because the map from A to C is surjective, so is the map from P to B. And now when you reverse arrows and say everything in terms of pushouts and compact quantum spaces, you will get precisely this condition, which was, I don't know, C3, I believe. Okay. And you can see that this is indeed the case, because remember that P is the subalgebra of compatible pairs in A plus B. Okay, so you take A plus B as an algebra, but you look only at these pairs which are compatible for these two maps. And because that map on the left-hand side is surjective, it's clear that no matter what B you choose, when you map it to something in C, but because this map from A onto C is surjective, there will always be something in A which will map to the same C to which your element in B maps. So this means that you will have, for any element in B, you'll have a compatible element in A, so that it will be in the pullback. That's why you'll have a surjection from P onto B. Okay, so I even proved it to you. Okay, so that's this axiom, and another axiom was about, maybe I should go back. Yes, weak equivalences are closed under gluing. Yes, weak equivalences are closed under gluing. That's a non-trivial one, but it's a theorem. It's a theorem that we proved in the previous paper. And let me sketch for you of how it works. So imagine that I have 2 pullback diagrams for sister algebras. So here I have some A prime, B prime, C prime, and I no longer demand any map to be surjective. And here I have a pullback sister algebra P prime. Okay, and now imagine that I have a star homomorphism from C to C prime, that I have a star homomorphism from A to A prime, I have a star homomorphism from B to B prime, and then of course it induces a star homomorphism from P to P prime. This is the universal property of the pullback. Just let me correct the subjectivity. I no longer assume that anything is subjective. So I erase this double head here and there. Okay, and now if it happens that the first 3 arrows from C to C prime, from A to A prime, and from B to B prime, if they induce isomorphism on K theory, then so does the induced map from P to B prime. And you can prove it in the standard way using the Mayer-Ettore 6-term exact sequence in K theory, using the 5 isomorphism lemma, and using the functoriality of K theory. And well, this is the only place where it becomes, well, I don't say demanding because it's easy, but when it demands some work from you, you must know the explicit connecting homomorphism in your 6th-term exact sequence in K theory. Once you have explicit formulas, you can just verify that everything works. So this way, we verify axiom W3, as a simple theorem in the K-theory of C-star algebras. And as you perhaps might expect, proving the CW axiom in this category, this Wellhausen category of compact quantum spaces, that's actually a bit of work. So I think we have like 2 pages of a proof. But again, technology is standard. You know, you'll use the usual magic of the homological algebra of K-theory, and you prove it. Okay, but that's lengthy, and I think that this is completely new. All right. So this is about the theorem, and this is my first take-home message for you. This is a certain general result. We realized that in what we are doing, we're doing something very similar to Wellhausen, and then we wanted to formalize it, and we formalized it in a way that I just explained. But what we are really after is that when we are in our beloved category of compact quantum spaces, then it is a CW Wellhausen category, and all axioms hold, with 5 of them holding trivially, 1 being an earlier theorem, this W3, and CW being a new theorem. Okay, but this is the first theoretical result, and it will later on help us, for instance, to compute K groups. Okay, now let me recall you. So I realize that now I'm offending your intelligence because everybody remembers from the kindergarten what the CW complex is. But let me recall it nevertheless, so that you see how I modify it to become quantum. And we're interested only in finite CW complexes. So a finite CW complex is a topological space X admitting a sequence of closed embeddings, which we refer to as filtration by skeleta. So you start from something finite and discrete, and then you end up with your space. And this is a sequence of closed embeddings, and they have increasing dimensions. And I think you can talk about the covering dimensions for these topological spaces. But what is very crucial is that these closed embeddings are not just any closed embeddings, that they are obtained by so-called attaching cells. So that these closed embeddings are defined by certain push-out diagrams, okay? And first I have spheres and I have balls, and everybody knows that balls are boundaries of spheres, and these are our cells. All these balls and spheres have their dimensions. They are manifolds after all, although we treat them as topological spaces, but the covering dimension is what it should be. And we have the following push-out diagram, as you can see here on the picture, right? The reason why I have this complication of having disjoint union of spheres and disjoint union of balls, and here, by the way, I should write that this is the disjoint boundary map, embedding S as the boundary of a ball. We can have many cells attached in one dimension. Okay, nobody tells you that it's only that when you fix your dimension, you attach only one cell. You can attach many cells. So in general, you'll have this coproduct, this disjoint union of spaces. But in our examples, this IK will be simply equal to 1. But in general, IK varies as K varies. Okay. But what is very important that this attachment of cells, well, this gives you a push-out diagram. So you somehow you map a sphere on something in the lower dimension, but then you extend the sphere, you fill up the sphere with the ball, okay, and then somehow you mimic this procedure at the site of XDs, and precisely speaking, the moment these maps are defined, the maps at the bottom, so the maps from the spheres to XDK minus 1, and the maps from the and the canonically given boundary maps to the balls, then you can take the push out, and what we demand is that this closed embedding that we have in this filtration by skeleta is given by such a push-out diagram. Okay. All right. So this is the classical CW complex, and now in order to define for you a quantum CW complex, I have to define what I just baptized quantum K balls and quantum K spheres. So this is here where our work is completely different from the work of Ehlers and others, because they define some non-commutative CW complexes. And this is why we stay clear from this name. We call it quantum CW complexes in order to avoid confusion, although we would prefer to call them maybe non-commutative CW complexes. But the point is that our cells are really purely quantum and really arbitrary. We give them axiomatically. We just want them to satisfy some K-theory properties, and then that's all we need. It's sufficient for our definition. Whereas Ehlers has some very concrete, very limited models for what cells can be and what attaching of cells can be. All right, but let's be more concrete. So classically, when you look at the family of spheres and balls and the boundary maps, including spheres and the boundaries of the balls, they enjoy a number of very concrete K-theoretical properties, right? I mean, they induce, and they depend on dimensions. So spelling it out would be too complicated. This is why I took it out. But these are the obvious properties that you have for balls and spheres in K-theory and for the boundary. Okay. And then you extract all these obvious properties that we know from high school about the K-theory of balls being bounded by spheres. And then you take it as axioms for your unital sister algebras. I'm not going to spell out these axioms. It would take too long, and they're not very enlightening. These are very elementary axioms. Okay, let me tell you by, and these axiomatically given sister algebras, I mean, any family of sister algebras which satisfies these K-theory axioms that we mimic from the K-theory properties of inclusions of boundary spheres in balls, that we call a quantum K-sphere and a quantum K-ball. Okay, and the map between them, which I denote by the same symbol of Tweedledee, is the boundary map. Okay. But I want to give you an example so that it's not something completely bizarre. Well, when you look at the Waxman-Soibelman odd quantum sphere, you know that they are bounding the Hong-Szymański quantum balls. And this boundary map satisfies all axioms. This family satisfies all axioms that the family of classical balls and spheres and the inclusion satisfy. Okay. And now I should explain to you what I mean by this natural inclusion. And it's best done in terms of graph sister algebras. So these inclusions of quantum spaces comes from inclusion of graphs. So if you look at a Waxman-Soibelman quantum sphere as a graph sister algebra, it has the following graph. Well, let me write it down in dimension 5, but it works in any dimension. Otherwise, it's too complicated. So I have 3 vertices. At which of these vertices I have loops. And then from any vertex on the left, I have an edge going to a vertex on the right. Okay, so this is the graph of the graph sister algebra of the 5 sphere. Now, what is the 6th ball? Well, you now have 4 vertices, but on the first 3 of them, you have loops. And then the story is as before. You have edges going from leftmost, from any vertex on the left, you have an edge going to any vertex on the right. So I have an arrow here, and I have an arrow here, and I have, oh, sorry, so, and I also have an arrow here. So I guess this one was redundant because we already have it. Let me erase it. This was stupid. Of course, this one is already taken care of. We go from 1 to 2, we go from 1 to 3, and we go from 2 to 3. Yes. And here we have 4. So we also go from 1 to 4, from 2 to 4, and from 3 to 4. Okay. So that's this inclusion of graphs. And when you have such an inclusion of graphs, you have going in the opposite direction star homomorphism of graph sister algebra. So now I'm going to take a graph sister algebra of such a graph. I have a star homomorphism going in the opposite direction. So now when I reverse the direction again, it means that indeed I just told you a nice cofibration from S5Q V6Q. Okay, so that's what gives us first family of K quantum K spheres, and another family, well, is in the same fashion. Instead of taking balls, I take polydisks, quantum polydisks, which are given to me by tensor powers of a Teplitz algebra. And then the HAJAC sphere can be defined. I mean, that's not the way we defined it, but it's an equivalent definition. It can be defined as the quotient of the nth tensor power of a Teplitz algebra by the nth tensor power of the ideal of compact operators. Okay, you can think about it in the following way. This is a polydisk, so this is you take a two-dimensional unit disk and you take its nth Cartesian power. So topologically, this is a 2n ball. But now, when you think about such a power of compact operators, this is exactly the inside of this ball. So when you divide by the ideal, you remove the inside of this ball and you just get the boundary sphere. And this is the HAJAC quantum sphere. Okay, so this star homomorphism gives me an inclusion of a 2n-1 HAJAC quantum sphere into the nth polydisk. Okay, here I write n not to n because I mean it as the Cartesian power of dq, and the dq is always, so to say, two-dimensional. All right, so I gave you a definition and I gave you examples. I hope it's enough. And now we can come to the definition of the day, I mean, second definition of the day, of what it is that we mean by a finite weak quantum CW complex. Because this is how we're going beyond the naive. This is solving the puzzle of the multi-Poolbeck quantum complex projective spaces. Okay, so a finite weak CW complex is an object X in our CW Waldhausen category of compact quantum spaces. That's what we already introduced via the theorem. And it must admit a sequence of weak cofibrations. So we see this definition of weak cofibration was absolutely crucial because this is what gives us weak filtration by skeleton. As before, we start from xd0 and we end up with our object X, okay? And now these weak cofibrations, they must be of a specific form. Okay, remember that the weak cofibration is a composition of a cofibration and the inverse of the weak equivalence. Okay, so I go from xdk to xdk tilde by a cofibration, but then I also have a weak equivalence from xdk to xdk tilde, and this is what I invert. And the composition of these two arrows is precisely my weak cofibration. But now it's not just any weak cofibration that I want, just as in the classical case, it's not just any closed embedding that I want. I want these cofibrations going to the tilted object to be determined by the push-out diagram. And here, this is precisely as we had it for the classical CW complex, only now I'm replacing topological spaces and classical topological spheres, topological balls by our quantum K balls. And the story is exactly the same. I must have that this cofibration, which defines my weak cofibration, necessarily comes from such a push-out diagram, which is given by attaching cells, all right? And we assume that the first sister algebra of xd0 is finite dimensional, so it's a finite quantum space, right? So covering dimension, if you want, is 0, so d0 is equal to 0. And then we have a sequence of increasing natural numbers. But here, that's, I would say, is a weak point of this definition. We don't have any concept of a dimension. Of course, we have dimension theory for sister algebras. And of course, we know that the nuclear dimension of a commutative sister algebra is the same as the covering dimension of the underlying compact house of topological space. But here for us, these decays, which were dimensions classically, these are only markers. So this is only for us to establish some hierarchy. And in examples, these are simply dimensions before the quantization. Okay.
So the parity of the dimension still matters.
Oh, yes. Yes. Yes, that's true. But this is hidden. Thank you, Francesca. It's a very good point. But this is hidden here in this definition. Sorry, in this definition. No. Where are my K balls? Here, right? It's hidden here. I just wrote it, enjoys very concrete K theoretical properties. But these K theoretical properties depend on parity. right? I mean, K-theory of an odd sphere is quite different from the K-theory of the even sphere.
Yeah, and the point is that K-theory only see the parity of the dimension of spheres.
Yes, yes, and that's yes, exactly. So we don't exactly. So in a way, this is not so tragic that we lose this concept of a dimension that we have in the classical setting. What we retain is the fundamental thing, which is parity. That we retain. What we lose is that it comes from something of a given dimension. You see, in the relative case, if you take, say, compact operators and you tensor product them with themselves, this is just, again, compact operators. So if you think about this as quantum plane, R2, well, classically, if I have R2, Cartesian product R2, I get R4. This is not R2 again, you see? So in the quantum world, this tensor product, which corresponds to the Cartesian product of spaces, that's working differently. So here we just retain parity, but we lose the very dimension. Yes, Adam?
May I have a question?
Sure.
So even for these building blocks being very general, yes, quantum balls and quantum spheres, even for those building blocks, you don't in fact have a notion. One shouldn't expect, yes, am I right? One shouldn't expect the correct notion of a dimension, even for the building blocks, yes?
Yes, exactly, yes, of course, yes.
You allow arbitrarily, possibly very exotic.
Exactly, yes. And in fact, there is one example I'm not going to talk about, which is different from the classical setting. It doesn't have a classical counterpart. When you go to weighted projective spaces, you can have a nice finite quantum CW complex structure, but this is a quantum effect. You can construct your Push-out diagrams, or if you want to be honest and precise, well, it's actually precise, but if you want to be honest, this is just pullbacks of sister algebras. Then these pullbacks are non-trivial. They give you new spaces only when you are quantum. In the classical setting, this is just tautology. You extend by identity. Of course, the identity map is a closed embedding. So I could artificially write some stupid sequence of closed embeddings being identity maps. That's not a very exciting CW complex structure. But in the quantum world, these spaces that are homeomorphic in the commutative setting, in the classical setting, they are no longer isomorphic as sister algebras. They are, if you want, non-homeomorphic as compact quantum spaces, and you have some exotic CW complex structures. And then the dimension is lost. I mean, it's not like I'm attaching higher dimensional sets. No. I basically keep the same dimension. I only care about parity. Now, can I erase this? It's so annoying that some marks that I make, I cannot erase. Anyway, okay, and now another important part is that I have two definitions in one go. So note that if we drop this word weak everywhere, and if we take this weak equivalence here to be just the identity map, then this is exactly that we obtain the definition of the finite quantum CW complex without this word weak. Or if you want, we can call it a strict quantum CW complex. Okay. All right, so this is the second definition of the day. I'm looking for my pen. Yes, here it is. Okay, so here we can take identity and drop weak everywhere. And then instead of weak cofibration, we'll just have cofibration. The tilde will be unnecessary. Okay, so this is exactly what we had to do in order to accommodate this multi-pullback deformation of complex projective spaces. Okay, now I promised you some examples in my abstract, and here they are. This is really nice because these are not our examples. Well, when you develop a new theory, of course, you are searching for examples, or you often develop new theory in order to solve some SSR questions related to concrete examples. But then these examples and the theory are just by the very nature interrelated. They are born together. They are, you know, came from the same womb, so to say. But now this is very nice to discover that somebody else's work, which was completely detached from what you are doing, it's actually a beautiful example of what you're doing. And there is a paper of Garcia and Wagner, these guys from Mexico, who defined a certain class, I call them Teplitz compact quantum surfaces. These are deformations, if you want, quantizations of the compact Riemann surfaces, both orientable and non-orientable. Okay, and they have a definition of what these sister algebras are, but they give these definitions in terms of pullbacks of sister algebras. So they played into our ballpark immediately, and because of what they proved is that they have certain pullbacks, they're even defining pullbacks of sister algebras, and then in our language we have the push-outs in our category, and then you can check that everything holds water. And I already told you that for me this is a nice model for K-spheres and K-balls, right? Because Waxman-Soibelman in dimension 1 is just the usual circle, and Holm-Szymański in dimension 2 is the usual Klimek-Leśniewski quantum disk. So that's the family I already told you about. So it fits beautifully into our definition of a finite quantum CW complex. And indeed, here's your filtration by Skeleta. You just have something trivial in dimension 0 at just 1 point. And then in dimension 1, you have this, how is it called? Bouquet of circles? I forgot the name for this symbol.
Wedge.
Wedge.
Wedge sum.
Wedge. You have this wedge sum of circles, okay? And this is what you have in dimension 1. So
bouquet is also correct, I think.
Bouquet is also correct, right?
I think so.
Okay, there's some.
1 point union, bouquet.
Yes.
Wedge.
So this was very gratifying to see that somebody else's examples fit perfectly on the nose into our definition. We could claim this territory as our own. So we eat fruits from somebody else's garden. Okay, but it's, and again it froze. Okay, so now somebody wanted me to define multi-pullback. Oh my goodness, I forgot to correct an error. There is an M missing. It's not alti-pullback, it's multi-pullback. Okay. So this is not the way Bartek, Natabek, Kaigun, and I defined them. We discovered them from a completely different principle, which would take too long to explain here. But a quick and easy way to define them is the following. For us, in our paper, this is a theorem. They can be given as fixed-point sister subalgebras for HAJAC quantum spheres. And that's from the paper with Richard Nest, Aidan Sims, David Pask, and Jan Rudnik, and Bartek Zieliński. I forgot that. Maybe I put, this is a long paper in JNCG, but definitely with Richard Nest. And there we proved that, in fact, what we defined with Bartek as multi-pullbacks, whence the name multi-pullback quantum complex projective spaces, because our defining principle was the principle of gluings, of defining certain sister algebras by complicating multi-pullbacks. But when we unravel these multi-pullbacks to be simply the fixed-point sister subalgebras of the HAJAC quantum spheres. And this is what we can take here as the definition. And I just defined for you, this is again not the way we originally defined it, but it's this time it's easily equivalent. So definition, because this here, which is an isomorphism in that paper, that's not easy. But of course, this is this isomorphism is very easy, because it's if you think about this HAJAC quantum sphere as something being defined by commuting isometry satisfying one equation, then you immediately see that you have an isomorphism with this quotient of the tensor power of Teplitz algebra by the tensor power of compact operators. Okay, so that's how we introduce them. And well, what good is a definition if it's not followed by some important result? And here we have a result which I value a lot. I call it a tubular neighborhood lemma. And it says the following, that if I take any natural number, 0 included, and when I take any positive natural number, so 0 excluded, then the U1 equivariant map, which goes from the sister algebra of the HAJAC quantum sphere in dimension 2n-1 tensor with the Teplitz algebra k times, that this map going to, again, the sister algebra of the HAJAC quantum sphere in dimension 2n-1, but now tensored with the Teplitz algebra k+1 many times. So if you want, the left and the right sister algebra differ simply by the fact that the right hand side sister algebra is the left hand side sister algebra tensored with the Teplitz algebra. So this map makes perfect sense. I'm having identity on the first tensorans, and I just have the unit map on the right node, because of course I can always write here tensor with C. And you see, Paul, that's exactly what I told you earlier, that for us, a key example, key building block, our atom, our basic molecule, is the unital map from the sister algebra of complex numbers to the sister algebra of Teplitz, to the Teplitz sister algebra. Okay?
Yes.
That's just the unit map. And then, of course, I can sex it up to have such a map like here, right? And when I say that it's U1 equivariant, it's U1 equivariant for the standard diagonal action on the HAJAC quantum sphere. You can also think about the HAJAC quantum sphere as higher rank graph sister algebras, and then you have the gauge action of a torus on such a higher rank graph sister algebra. And then when you put your circle diagonal in the torus, and then you take the gauge action of a torus, that's the action that we are talking about. Okay, but it's important it's diagonal because you also have a Teplitz algebra. So I'm rescaling my isometry by a unitary number, the same unitary number at each tensoran. So that's for the diagonal UN structure here. All right. I claim now that this. So of course this map is equivariant because identity is equivariant, and the unit map is equivariant. So that's the UN equivariant map star homomorphism of sister algebras. But when I restrict it, so I can of course restrict it to the UN fixed point subalgebras, right? Any equivariant map of sister algebras can be restricted to fixed point sister subalgebras. Okay. And when I say restricted, I mean restricted in the domain and restricted in the codomain. So now I have a map from the fixed point sister subalgebra to another fixed point sister subalgebra. And I take this map and I claim that this map induces an isomorphism in K theory. And this is one of our key technical results. Francesco, would you agree?
Yes, yes.
That's exactly what we proved in Naples. And this was very important. This was like one of the biggest stumbling blocks which we needed to overcome. And as you can imagine, this is exactly what we need to get our CW Waldhausen category.
This was last proof before COVID.
Yes,
last
exactly.
Proof in person.
Exactly, yes. Well, but then we have a new proof in person when you came to Warsaw in September. For instance, this example I showed you, this is what we did in September when you and Bartek came to Warsaw. But yeah, true, this was in January and the COVID outbreak was in March. All right, so now I want to tell you in what sense this multiple quantum complex projective space is a weak quantum CW complex. So by this tubular neighborhood lemma, you can now define a certain C-star algebra whose underlying compact quantum space we denoted by tilde CP and T. And from this lemma, we not only have this new C-star algebra, but we also have a weak equivalence. Yeah. So in other words, what I have a certain map of C-star algebras going in the opposite direction, which induces an isomorphism on K theory. That's a complicated definition of a CP and tilde. Let me skip it, but it comes from this lemma. We wouldn't have it with this tubular neighborhood lemma is what allows us to define such a weak equivalence. Okay. And then not only we have such a sorry, is it? Yeah. Not only we have such a weak equivalence, but also we have a push-out diagram. So if you want pullback diagram in the category of unital sister algebras, which is of the following form. Remember, I gave you this as the second admissible family of quantum K balls and K spheres, right? Now I'm having HAJAC quantum spheres, and I have my polydisks instead of quantum balls. And they again satisfy all the desired axioms in K theory, and they are sensitive only to parity. The actual dimension is irrelevant. They are sensitive only to parity. Okay, and now we can wonder what, well, I told you already what this Tweedledee map is, the boundary map is. We defined it. That's just dividing by compact operators if you want. This H is the defining map because I basically defined CPN minus 1 T as the quotient of S to N minus 1 H by the action of U1. So this is the defining map for CPN minus T. And well, once I have these two maps, the defining map and the given map, then I can take the push out. I take the push out, and well, because you can check that delta is a cofibration in our Cerebral-Wellhausen category, and our category is a Cerebral-Wellhausen category, so there also must be a cofibration. Okay, and did I say it correctly? Yeah, this is a cofibration, yes, and this is a cofibration. Okay. Yeah, sorry, yes, of course. I tilde is a cofibration, yes. I tilde is a cofibration. So now what we can do the following. Let me see, is it written somewhere or should I draw it? Yeah, this is written, wait a second. Okay. It's somehow strange that is used the weak vibration by skeleton. Where is? No, I'm missing something. I have to write it down, I'm afraid. Okay, so now I want to explain to you this weak filtration by skeleton. So I have to tell you in what sense I have here weak cofibration. Well, you only have one hero, CPN minus 1 T, and here take the other hero, CPN without minus 1 T. And here you have the psi. You have this weak equivalence given by the tubular neighborhood lemma. So now you can guess what is our weak cofibration. I compose I tilde given by this push-out diagram with the inverse of my weak equivalence. So I tilde composed with psi inverse. Sorry, the other way around.
The opposite,
sorry. Yeah, psi inverse composed with I tilde. This is exactly our weak cofibration, which gives me this weak filtration by skeleton, rendering CPNT a finite weak quantum CW complex. Okay, and as a result of having this CW complex structure, we can very easily compute the K theory. But of course, I have to say that initially the K theory was computed by Richard Nest in our joint paper in a very smart way. His proof is very ingenious and very beautiful. I don't know, Paul, if you remember, but for many years when I was coming to Penn State, I was bothering you and Nigel. Definitely, Nigel, how do I compute K groups? I'm giving you very simple sister algebras, not in the mathematical sense, easy sister algebras. And I'm asking you, what are the K groups? And it wasn't obvious how to compute even the K groups for these multiple quantum complex projective spaces. But then Richard came to Warsaw and he had a very, very beautiful, very geometrical idea of how to compute these K groups. And he did it, and it's published in our joint paper. But now, if you combine this first theorem telling us that indeed the category of compact quantum spaces satisfies these Wellhausen axioms enlarged by our CW axiom cofibration weakening, when having this in mind, you can prove certain very general statements for any quantum K balls and any quantum K spheres. You can prove very general statements for K theory. And once you have these general consequences in K theory for all weak finite quantum CW complexes, then it's just plug and play. When computing these K groups is a matter of half a page. You just plug it into the general theorems and you are done. Okay, so sort of what Richard did in one go, this is one beautiful proof. We separated into two steps. One conceptual, completely general part, and another one case related. It somehow reminds me of a calculation of K-theory of quantum RP2 with Wojtek Szymański. First, we published a paper, and Rainer Mattes. First, we published a paper in which we just have an elaborate proof, lots of nice sister algebraic tricks, phases of elements in the sister algebra, power decompositions, whatnots, spectra, lots of stuff, and lo and behold, we compute the K group. But then Wojtek Szymański realized that the quantum real projective plane is a graph sister algebra. And for the graph sister algebras, we have a celebrated Rabin-Szymański theorem of how to compute K groups from graphs. And then you have this general theorem of how to compute K groups from graphs. And then you have this case-related theorem saying that, aha, for such and such a graph, that sister algebra is its graph sister algebra. So this was split into two cases. So here we do something similar to the proof of Richard Mest. We split it into completely general part, which works at an extremely mind-boggling level of generality. And when we plug in the specific case of this multiple quantum projective space sister algebra, and with a few more lines, we get there. Okay, so that's the theorem, which is a byproduct of having this weak quantum CW complex structure. And well, this is, in a way, you can say it's independent of the CW complex structures of these both quantizations of complex projective spaces. But technically, this is true. I mean, strictly speaking, this is true. We are not citing any concrete result and saying, all right, voila, as a corollary, we get this theorem. But, you know, it comes from the study of the pullback structures. You study the pullback structures of Waxman-Soberman quantum spheres, and you study the pullback structures of the HAJAC quantum spheres. And it's precisely the study of pullback structures which led to the CW complex structures of the fixed point sister subalgebras of quantum projective spaces. Okay, so that's sort of playing in the same ballpark. All right. But formally speaking, we don't need it. It is an independent theorem. But this is, again, I emphasize, this is a theorem that I think Francesco proved even before I came to Naples. I don't remember. But anyway, this is a theorem that is possible because you have these iterated pullback presentations, and you define this homomorphism omega n inductively, and then you prove this theorem by induction. But just as for the tubular neighborhood lemma, this induction requires some work. So that's a serious theorem, which does not utilize the concept of a quantum stable complex structure, but it's very closely related to it. Its proof is very closely related to it. We wouldn't have such a theorem if we didn't dive deeply into the pullback structure of these quantum sphere sister algebras. Okay, so that's the theorem. I take any natural number, and I take a yes.
So can you just recall like how you inductively define the HAJAC sphere 2n+1 inductively by pullbacks? Or like
okay, this would take a while, but okay, let me try to do it in the low dimension. No, that's this is what Alan Kohn always does. He has the simplest non-trivial example, and he says, look, this is cyclic homology. This is cyclic cycle. So let me answer your question in this way. So for n equal to 1, you have a 3 quantum sphere. This is the SUQ2 sister algebra. And you can write for this the following pullback diagram. So here you have the sister algebra of SUQ2. Well, you wanted quantum groups, you have quantum. And here you have Teplitz tensor of the circle, so C of S1, and here you have just C of S1, You see, S1 is a quantum subgroup of SUQ2. That's his map. And here we have the classical torus. Okay. And it's obvious how this is killing off diagonal generators in SUQ2. That map is a bit involved. So this is the only map which is a bit tricky. All right. So for instance, in order to generalize it, because now everything here is given by graph sister algebras. Well, maybe tensor products of graph sister algebras included, or you want to go to higher rank graph sister algebras. So you're wondering, how do we do it in arbitrary dimension? And then using graph sister algebra representation, we managed to guess it. And this is what led to our trimmable theorem. And this was the first proof which I got with Francesco and Mariusz and Francesca for this pullback structure of CP and Q for all ends, all right? But we started from spheres. So now we go to HAJAC. So that's what Paul and I were doing in Mittag-Leffler. I mean, this was, we twisted it. We twisted it by some theta deformation. This is what we did to it. But originally, this idea comes back to Kalov and Mattes. But okay, let me write it down. CS3H. And this is the following pullback diagram. See, the only difference is that here you have C of S1 tensor Teplitz. And here you have Teplitz tensor C of S1. And here you have again C of T2. Well, the maps are obvious, because here you have on one circle we go the symbol map, on the other circle we go the identity, and here on one circle we go with identity, on the other circle we go with the unit map, and here is also obvious. And now, well, you see, just as before, what I do, I tensor it with complex numbers. Okay, here I have the identity map. Here I have the identity map. And here I have identity tensor of this map, which is the unit map from C to the Teplitz algebra. Everything commutes. And of course, very easily by the Kinath formula, you very easily conclude that this map going from CS1 to CS1 tensor Teplitz, that this map induces an isomorphism on K theory. Okay, and then we know that this map, given here, the induced star homomorphism also induces isomorphism on K theory. And then you go up, because this is your lower dimensional sphere, this is your higher dimensional sphere, and then you go up. But it's a bit complicated, because the multi-pullback structure of a HAJAC is more complicated. So that's not so simple. But that's in dimension 3, this is what happens. Okay?
Okay, yes, thanks.
Now, how do I erase it? Okay, it works. But I wish it were more efficient. If I write on the Zoom whiteboard, it's far more efficient.
Maybe it's like you encircle what you want to erase.
Okay.
Oh,
okay. Okay, it's really like digital talk. You have to sweat to erase it. But this is a bit annoying. But okay, this is exactly why I wanted to give my talk using Drawboard PDF, because this way I can answer such questions. Okay, so here I have this theorem. So you have this star homomorphism, which is defined inductively. And you can check that it induces an isomorphism in K theory, but that's maybe not such a big deal. Okay, well, these K groups are simple, it's Z and Z. But moreover, its restriction to U unfixed point subalgebras induces also an isomorphism on K theory. And that's something very important, because not only the K theory of CP and Q and CP and T are the same, that's trivial. I mean, this is the same as the K theory of, I don't know, n+1 point space. So just equality of K groups means nothing. What is very important is, and this is what differs us from KK theory, you see, In KK theory, n spaces would be KK equivalent to CPN. Something, you know, discrete, disconnected, trivial, because K theory is the same. I mean, it just counts the number of points, right? If you have n plus 1 many points, or you have CPN, the K theories are the same. But these two spaces are totally, completely different. So KK forgets too much. So that's our philosophy. This is why we went into this Waldhausen. If you just have star homomorphism, that's not good enough, because some star homomorphisms that you desperately need, they refuse to exist. So you force them into existence, but in a more general setting. But then you don't want to be too general, because if you take the category of sister algebras in which elements of KK group are your morphisms, of course, you have such a category, is very important, then you have too many morphisms. You identify things that are too different from each other. Okay. All right. So in other words, this theorem proves, and again, I would say that this is a non-trivial theorem. This is a lot of work to prove it, and you do it by induction, and you do it analyzing this multi-Pullback structure, which, if you want, is the CW complex structure in disguise. So that's not completely unrelated. And you have one fundamental upshot, because of course you can always wonder, so what is this theory good for? What concrete difficult problems did you solve using this theory? And I would point to this corollary. And I would point it to this because even classically, Paul, correct me if I'm wrong, if I give you a higher dimensional sphere, it's not so obvious what is the generator of K1.
You mean for an odd sphere?
Yes.
Well, that's by periodicity tells you that. Tells you.
Yeah, but can you, of course, but you can you give me a generator? I want an element.
Yeah, that's good. You can write this down using the Clifford very explicitly. Using Clifford algebra. Yes, this can be done very explicitly.
Very explicitly, but this is a complicated expression, right? That's not.
No, it's a very simple thing. It's a very simple explicit formula for matrices using the Clifford algebra.
And for the free sphere, that's just a fundamental representation of SU2, right?
Yeah. Well, that's the beginning case, let's say, for the free sphere, something like that.
Anyway, okay. So we have it nicely figured out classically. So I retract my comment. We have it very nicely done classically, and we would like to have much in the same way in the non-commutative setting. Now, for CP, for the Waxman-Sobelman spheres is no problem, because they're graph sister algebras, and we have extremely powerful theorems that tells us not only how to compute K groups, but how to find generators of K groups. And we have a very explicit formula for arbitrary graph sister algebra of how to find generators of K1 of my graph sister algebra. When we apply this general theory of graph sister algebra to the Waxman-Sobelman quantum sphere sister algebra, you get a very simple unitary in the sister algebra, which is a generator of the K1 group. But the same thing is not available on the other side. Well, you can say, all right, this is a multi-Pullback, not multi-Pullback, this is a higher rank graph sister algebra, but I'm not aware of such strong theorems concerning generators of K theory for higher rank graph sister algebras. Maybe they exist, maybe they don't. I just don't know them. And
so in particular, this generator lies in the algebra itself.
Yes, this is a quantum effect. Classically, it's impossible, right? That's like with power is light and potent. It's inside your sister algebra, not in matrices over a system.
Interesting.
Yeah. You can. One of the things you can prove, and I remember Paul, we were arguing for it in one of the lectures in Penn State, is that the K1 generator of higher dimensional spheres cannot be in the commutative sister algebra of the sphere. Yeah, that's one of the things you can conclude rather quickly. But here we have this.
Yes. Okay. Yeah.
Right. Okay. But here we have this quantum miracle that our K1 generator is in our sister algebra. But now, because of the theorem above, and because we can immediately write down and explicitly the K1 generator for the Waxman-Sobelman quantum sphere, well, we can just transfer it by this omega and map, and then of course, because it is an isomorphism on K theory, when a generator is not necessarily mapped to a generator. So what we obtain here is a generator of K1 of the sister algebra. And it would be very hard to compute otherwise. I mean, without some technology of higher rank graph sister algebras, which I don't know simply, and also, well, proving that this is a higher rank graph sister algebra, that's a proof basically due to Aidan Sims, is not so completely for free. We have to prove it. You use some theorems to prove it. It is not an observation that this is a higher rank graph sister algebra. So in any case, if you just take the sister algebra on the nose as the quotient of the Teplitz power by the compact's power, then I don't know how to find a generator. But here we have it in an extremely neat and explicit way. We take the generating isometries for this HAJAC quantum sphere, and voila, we write explicitly this element. You see, each of these are commuting isometries, okay? And each of them, of course, generates its own quantum disk. And basically, what we do, if you would take simply n commuting isometries, then the universal sister algebra would be the tensor power of a Teplitz algebra, right? But now we have to divide by the compact operators, and dividing by the compact operators is what I calling writing the sphere equation. And the sphere equation is that the following: if you take this product as in here, if you take this product as in here, but now you run it over all case from 0 to n, so include the n, and you have 1 minus sk star. So sk is isometries, but not unitars. Then this must be 0. That's the sphere equation. So that's not 0 because I'm multiplying from k equals 0 to n minus 1, not to n. All right. But that's the sphere equation. So if you want a presentation of a HAJAC quantum sphere by generators and relations, and this is how we were working on it. The only thing later on Paul and I did to this, we said that our two isometries, they do not commute. They commute up to a phase. So we theta twisted it. And that's what we wrote the paper about. And of course, the higher rank graph sister algebras can be theta twisted. And with Richard, we have all this theory of multi-pullback and HAJAC's spheres. We have it worked out also in the theta twisted case. But that's completely beyond the scope of this talk. So yes, so you have this universal sister algebra, and the only relation given by commuting isometries. Okay, so these are also relations. And the only, oh my goodness, it's 7 p.m. Okay, so I already extended it by 18 minutes. I will try to rush to finish it. And then that's the only relation by which we divide. And this is your generator. Okay, let's go on. Wow, that's the last slide. Oof. So that's okay. So that's something I'm not going to talk about. This is the sneak preview for Tomek's talk. So you see, when you do the K-theory of classical complex projective spaces, the way Atiyah Todd were doing it, and when Adams was working on it, you have the following beautiful theorem, which not only gives you the K groups. I mean, this is K1 is 0 and K0 is a free abelian group. When you look at it from the abelian group point of view, this is not too much. And as you know, because in general, when we do K-theory of non-commutative sister algebras, our projective modules are just one-sided modules. They are not bimodules. You cannot tensor them. So you are missing intrinsic natural multiplicative structures on K-theory. For non-commutative sister algebras, just does not exist. Like you know, the multiplication map, like the diagonal. Some things do not exist. They refuse to exist in the quantum world. But still, we managed to get around it. We managed to get around it and prove for both quantizations, for this multi-pullback quantization and for the Waxman-Soberman quantization, we managed to prove theorems which are very, very analogous to this famous Atiyah Todd picture of the K group of CPN. So first, you can view it as the ring of truncated polynomials. So as a generator, you take, so these L's here, and I see here's a mistake. This should be a straight L. These are associated line bundles. So you just take you take the defining Hopf vibration for CPN. So you go from S to n plus 1 to CPN. And this is, of course, a U1 bundle. And then you classify representations of U1 by the winding number. And with every representation, you have an associated line bundle, which is a line bundle over CPN. And here these numbers indicate the winding number. So LK is just the associated line bundle given by the winding number K. And the winding number gives us representation. Representation gives us associated line bundle. Okay, so this is what I mean here. And what has been proven that even as a ring, so here K0 is in a ring, it has an intrinsic ring structure. And we know that this is the ring of truncated polynomials. You take as your generator the K0 class of L1, you subtract 1, this is your variable, call it X. And then you take all polynomials, the integer coefficients in this variable, but you truncate it. You say that the n plus first power must be 0. And that's the ring structure on K0 CPN. And alternatively, you can also write it down that if you just look at the line bundles given by the first n winding numbers from n equals 0, when we have a trivial line bundle identity of the algebra to n, then this gives you a basis. So this is quite remarkable. And in particular, our CW complex structure picture allows you to see how you grow your generators of K theory. Because basically what happens is that you go from CPN to CPN plus 1. You will basically extend these line bundles from CPN to CPN plus 1, and then you have to add one more line bundle, which will be given by this higher winding number. But this higher winding number line bundle, you can prove that it all comes from the Milnor connecting homomorphism when you have this push-out picture defining your CW complex structure. So that's much deeper than just having a abelian group structure. We not only have generators, we not only geometrically understand generators, but also we get as close as possible to the Atiyah-Todd picture that is available in the classical setting. But this is yet another story which will be picked up by Tomek. Thank you very much for your patience and attention.
Great.
Francesco, you do the honor. Francesco.
Let's go.
Okay, Tomek, so you do it. I mean,
okay.
Yeah, sorry, I was in the toilet.
Francesco, continue. I just finished my talk, so you can now continue with your chairpersoning.
Yeah, okay, so thank you very much, Piotr, for the talk. And we continue with questions. You're still recording questions, right?
I'm still recording questions, so we are very much over time, but if you have some urgent questions, I will try to answer them.
Can I ask, like?
Sure.
Hi. So very interesting results. A lot of very interesting results. So
thank you.
Thanks, Piotr. Like.
I have a question. You have a certain Waldhausen category here.
Mm-hmm.
It was part of Waldhausen's idea that any Waldhausen category has K theory. There are K theory groups associated. Well, it's a well-defined thing for any Waldhausen category. You have a certain Waldhausen category. What are the K theory? What is the K theory?
I always said I don't know. I don't know.
Yeah, no. I'm just asking. I think this is an interesting question.
I agree. Tomek, maybe you can.
Yes, I can comment. In Waldhausen's original approach, these Waldhausen category is not the whole structure. You must have S operations which have to be used to define this K-theory. These are some complicated diagrams, and we don't need this because it was not our objective to define this Waldhausen category of spaces. So, in a sense, Waldhausen's category is the story about what is happening with K-theory before it becomes a functor taking values in abelian group. Okay, so it lives in some universal construction built with spaces, provided everything is embedded in some nice Waldhausen category. So it was not our perspective. Our perspective was the classical K-theory. But this gluing of spaces affects the structure of K-theory. And this part of K-theory, which can be detected computing K-theory, complex topological K-theory, was our main objective. So maybe in future we will consider the full Waldhausen's category, and we could speak about K-theory of sister algebras. But at the moment, any examples we had in mind didn't suggest such generality. Okay.
Mm-hmm.
Can you define for one of your quantum CW complexes its fundamental group?
No, and this is not about a fundamental group. So fundamental group is related to flat vector bundles, but this would require some additional structure. Okay, because the Tannakian reconstruction of the fundamental group from the monoidal category or Tannakian category of flat bundles requires an additional structure on these bundles, which is simply the flat connection. And then you can regard these flat connections as representations of fundamental group 2B. But they form a Tannakian category. And you can, after choosing the base point, you can have this neutralizing functor, the fiber functor, from automorphisms of which you could reconstruct the fundamental group at least up to profinite completion. But we are talking about the plain K-theory, where vector bundles are topological vector bundles without any flat connection. Okay, of course there's an approach based on differential K-theory. So this would be perspective maybe in which you could speak about the fundamental group. But on the level of topological K-theory, you don't have the relation between the fundamental group and K-theory.
Thank you. Can you say, given one of your compact quantum spaces, when is it simply connected? Can you say that?
No, because we don't. No, because we don't know what is the fundamental group, what is the universal covering, nothing. So introducing the fundamental group into this picture would require some additional structures on vector bundles.
Okay.
Like flat connection, kind of flat connection.
Okay.
So this can be done, but on the much deeper level of differential K-theory.
Okay, thank you.
Alex, go ahead. You had a question.
Yes, hi. So the CW Waldhausen categories that you define, like there is also some work by Uye I don't know what year, but I have a link like also, who is defining something that looks almost exactly the same as what you're defining, like but with unital replaced by just arbitrary star homomorphism. And this was like somewhat like the like shot off like to what some people did for like using like infinity categories. So they're talking about fibrant objects, and I think that's the same as like cofibrant stuff. So where you don't have a model category in the strict sense, like as a equivalent model category, but rather you only have one sort of like morphisms. And yeah, so this looks pretty much like what you did. So the CW Waldhausen axioms look exactly like these fibrant like, I don't know, fibrant categories or something like this.
So could you send me, please, a link to this paper?
Yes. So he did something exactly like, he wanted to define K-theory using exactly these localizations, what you also do. So I think it's this one. Let me just check that I clicked it right. Yeah. And there was like,
yes.
Yeah. And so what he did is like, so you can go from you can start from your category with cofibrant morphisms, right? You can then do some first localization that gives you like something like stable homotopy theory, but which is not exact yet, or is something like a triangulated category. And yeah, they did this, like they lifted it up like to the infinity categorical language and went all the way up like to do like their stable infinity categories and like and so on and so forth. And that was like something that started off like this. Okay, so this is particularly like pointed to C-star like as an application.
Yep. Thank you so much. We'll have a look.
Yes.
So I looked into this paper. So I can answer what's going on. So first of all, this paper uses some ideas of model categories. So our Waldhausen category, not our, in general, Waldhausen categories, two model categories are like upper triangular, like triangular matrices, two full matrices. Okay, Waldhausen categories lack these fibrations.
Yeah,
which for K-theory are completely irrelevant. So I think it's one of basic observation of Waldhausen. But in this localization business, there is some intermediate step. People usually speak about the Bausfeld localization, adding some weak equivalences, some more general than weak homotopy equivalences, and they prove that they form some appropriate class of mappings to be inverted, morphisms to be inverted. But to do this, you must have something about model category to speak about equivalence adjunctions and things like that. We do not have this.
Yeah, that's fine. That's fine, but that's exactly what he's doing. Like he's so they found like a weaker setup where you don't yet have a model structure, and that's also the case exactly for the category of C-star atlas, where you don't have a model structure yet. You have something strictly weaker, but and you can still do the localization.
He's building on homotopy theory, and he extends weak homotopy equivalences to equivalences of slightly more general form, which in our versions are K equivalences, morphisms inducing isomorphisms on K theory. Okay, but his perspective is higher categorical. He uses much more difficult things, but to achieve different goals. So what we are interested in was easy computing K theory. It was not in the direction of K theory of Waldhausen categories, as Paul said. Okay.
Yeah, that's also not what I mean. Like,
yeah,
I just mean like that there is already this notion of.
And if I remember well, he was working with pointed version.
Perhaps, yeah.
So in our situation, we have to work with unpointed version because our spaces, they are very rarely even have points.
Yeah.
Okay. Or very few points. So the position of the base point of our space is very sensitive inside of a quantum space. Of course, you can add a point formally to a compact space as a disjoint component, but then you have to work with reduced K-theory, and the story is completely different.
So but you say you use the unital case, right?
Yes, we are using, we are restricted only to the unital case, because in the non-unital case, it is not so much obvious which version of K-theory for locally compact spaces we have to generalize to the quantum setting. So compactly supported ones, or some representable, or some other versions. By no means it's obvious which would be the best generalization of embracing all our examples. Okay, so this and the main point in our CW Waldhausen categories is not Waldhausen story. It is this additional axiom, small CW, cofibration weakening, which allows us to construct weak CW structure. So
that's with the roofs, right? But that's with the roofs, right? Like, yeah, but that's what I mean. That's what Uye is doing. I mean, like, he's using exactly.
No. He's doing with different roofs, because in Waldhausen categories you can speak about morphisms by allowing some admissible epimorphisms and some admissible monomorphisms, and this calculus of roofs is a part of so-called Quillen approach to K-theory. Our roofs are different. Our roofs come from the calculus of fractions of these weak cofibrations as weak fractions.
Yes.
Yeah. So there are some similarity, because of course, if you speak about K-theory, all generalizations must contain this Waldhausen's kernel. But on boundaries of our generalizations, we are doing different things. Okay.
Well, with Waldhausen, his category, I think it was in fact CW complexes, maybe pointed CW complexes.
Yes.
That was his basic category. He was interested. Now, if you have some discrete group, you can form the purely algebraic group algebra over the integers, let's say, and you can take the Quillen K theory of that. So the algebraic K theory of this algebraic group algebra for any discrete group. Of course, you can do that. Now, Waldhausen introduced this idea that when you have a Waldhausen category, it has K theory. And I think his category was CW complexes, maybe pointed CW complex. Okay. But this category, he used this to extend algebraic K theory to CW complexes. That is, he defined for a CW complex its algebraic K theory. And in the special case, if the CW complex was the classifying space of a discrete group, in other words, a K pi 1 space, then it was just the Quillen algebraic K theory of the purely algebraic group algebra. So Waldhausen, using his ideas, he extended algebraic K theory to CW complexes. That is, you find a very interesting kind of algebraic K theory for CW complexes. And this was important for the study of what are called H cobordisms of manifolds. An idea of torsion for the fundamental group was introduced, and eventually this developed into what's called the Escobarism Theorem. So at any rate, you see, when you talk about the K theory of a C-star algebra, this, in Waldhausen's picture, this was the homotopy groups of the CW complex. And so there was a very interesting new kind of K theory that emerged from this. And so my question is, yes, of course, you are quite right. You used this in a very interesting way to do some quite interesting calculations of K theory, of what we usually mean by K theory, of a C-star algebra. But it might be the case that there is some interesting new kind of K theory that emerges from this. That's the point I'm attempting to make.
Yeah, thank you very much for this suggestion. Yeah, so if we start from this Waldhausen point of view, then the sky is a limit in generalization, because his theory is so general, embraces all these interesting examples which are not be computed by means of the usual K theory.
Mm. Right. Well, okay. So, thank you for these comments.
So I looked up, I mean, like, he does exactly this localization. I mean, like he has exactly these axioms, like for CW, Waldhausen category. I mean, like, I'm not referring like to Waldhausen's K theory, but like he does exactly like has this axioms, what is like listed here as like a CW Waldhausen category. And he takes exactly this localization with these rules. I mean, like, there's nothing more to it. I mean, like, if you just look up like the homotopy category, like, I mean, like, it's just a name, right?
But
I mean, like, it's not really like
what are his weak equivalences?
The isomorphisms in KK, I think.
Yeah.
Yeah. So not the isomorphisms in K theory, but the isomorphisms in K theory, in KK. And
in KK.
Yes, in KK.
So this is a completely different story.
Yes. So if you're in the non-nuclear, if you're not,
Piotr showed an example. Piotr showed an example of a space, finite space, n+1 points, which is KK equivalent to CPN.
Yes. I see.
So this K theoretical point of view kills topology completely, because cannot distinguish between spaces which are connected and are not connected. So what we allow to be inverted only are mappings between on the purely topological level. There are mappings of spaces.
They need to come from star homomorphisms.
Exactly. I emphasize
isomorphism of K theory.
Yes. So they need to come from star homomorphisms.
Yes.
You need to start.
So so look, in the classical situation, such a morphism must induce an isomorphism of rings. If you take into the consideration the ring structure, then you could easily distinguish this n+1 point space from CPN.
Yep.
So our equivalences do not glue spaces which shouldn't be glued from the and which are glued by KK equivalences.
Yes, I see.
So his approach with passing to KK theory is too radical, because spaces form a very non-linear category, very non-additive category. But KK is even a triangular category. It's a very brutal additivization of the category of spaces.
Yes, yes.
which
yes.
forgets almost all topology.
Yes.
Okay, so we are stick to the classical meaning of topology more than people using KK theory.
Yes.
Yeah.
Your maps need to really come between the spaces. Like
Yes.
Yes. I also had another question. Like, so you had this nice result about like the generators for K0 and K1 for the HAJAC spheres, I think. So like I looked up like the definition and the generators for the K0 and K1, like they seem like to be somewhat like very similar to like X-Lacka algebras. And like, so I wanted to ask, like, is there any relation?
I have no idea what, I know Lacka, but I don't know what he wrote about it.
So yeah, so he has also these products of, so kind of like intersections instead of sums like that. And so I thought that maybe there is like some relation.
I do not deny it. I have just no idea. I would have to look it up.
Because he also has these, I think they have a very concrete representation of the K0 and K1 for such X-Lacka algebras, like in terms of generators coming from the, like in terms of the generators themselves. Maybe it would be like, yes, okay.
Yeah, I don't deny it. I just don't know if this works. Yes, I cannot comment. Okay, so Francesco, you had to go because we're closing his department. So just let me continue. Any other questions, or should we call it a day? I think we should call it a day.
If we have two finite CW complexes, let's say, in the classical sense. And just as abelian groups, the K theories are isomorphic. Somebody gives us an isomorphism of the K theory. Does that imply that they are KK equivalent?
Yes.
It does imply it?
Yes, because corresponding sister algebras are UCT.
KK equivalent? Yeah?
Yeah.
That's a true, this is a true fact. This is
a true fact, yes. For classical,
you were saying earlier. Yeah, the point is you don't need a map. It's just if they are just isomorphic, just as abelian groups, that's enough.
Yes, to have a KK equivalence.
But in the UCT category, right?
Yes, UCT plus some assumptions. Maybe Francesco could.
He's gone. Francesco's gone.
He's gone, but we discussed this. But I forgot now what are additional assumptions. But classical spaces, locally compact space, even compact spaces satisfy all these conditions.
Well, let's say, suppose we take CPN and we just take a finite number of points.
Yes, they are KK.
The spaces are KK equivalent.
Yes. So I told you twice.
Your point about brutality, that the brutal aspect of KK theory.
Yes, because KK morphisms can be regarded as generalized correspondences.
Yes, correct. Yes.
But these correspondences are very discontinuous. So they cut spaces as it is prohibited in topology.
Good.
Into pieces and recollect the K theories from this data, but they say almost nothing about topology.
Okay, thank you, Tomasz. Yes, good.
So this is the main objective of our paper.
Yeah.
To rescue classical algebraic topology.
Yes.
From this brutality of KK theory.
Yeah, right. Okay, very good. Thank you, Tomasz. Okay.
So maybe to wind it up, let me emphasize things on my last slide. You see that here we are using these groupoid presentations and the theory of associated non-commutative vector bundles. So we need some new technology, and this groupoid presentation, that's the work of Albert. It is extremely beautiful, and this is how he could obtain some identities of this sort, and he could identify certain projections in a sister algebra as representing associated line bundles, and then we could prove such identities. This is a lot of non-trivial work, many calculations, because you see, we do not have this intrinsic ring structure, so we cannot say, okay, this is a ring truncated polynomials, I can compute the inverse. No, it's sort of the other way around. First you do these dirty calculations, and then you see, aha, so now I can bundle it up together and I can introduce some non-intrinsic ring structure. But this is very beautiful. It's much deeper picture of K0 group than just saying that this is a free abelian group. And this is very geometric, and we have it all in the non-commutative setting. And but then we go even further, and this is a recent invention of Tomek. It turns out that if you use the theory of associated non-commutative vector bundles, when they are given not only by projective modules, but by bimodules that are projective on both sides, and you can finally make the tensor product. And somehow what happens is that you take your you make your K0 group, your abelian group, it now becomes a module of a representation ring of some compact quantum group, which yields associated vector bundles over your sister algebra. And it turns out that this additional structure allows you somehow, in a way which Tomek will explain in January, allows you to rescue this multiplicativity of K theory. And we are after this, again, to save us from the brutality of just having abelian groups, to distinguish topological spaces that are very different. But I'm very happy about these two methods, because one of them is very close to my heart, because it's a theory of principal comodular algebras, scopical extensions, what we are doing called free actions of compact quantum groups and unital sister algebra. Somehow you define some additional continuity using compact quantum principal bundles above your sister algebras. So that's very exciting for me, and it seems to be working. And the groupoid presentation of Albert, that's also a lot of magic, and this is very quantum. So that's for me quite remarkable that such a totally quantum approach, which is totally unavailable in the classical setting, actually led us to these Atiyah-Todd identities. And really, this is my final comment, and then we stop recording. But let me say it. I just need a pen. And of course, I cannot find it. Yeah, here it is. So you see, the story is the following: is that first you take your TEPI's algebra, its tensor power. Of course, it has lots and lots of projections, but they're all trivial in K theory, right? The K theory of tensor power of TEPI's algebra is trivial. Well, you divide it by compact operators, so you now have equivalence classes of projections. Well, but the K theory of this quotient sister algebra is also trivial. Everything is given by one in your algebra. So all your fancy projections can be conjugated away. But now you go to the fixed point. You go to the projective spaces. And these projections are no longer trivial in K theory, because things that were conjugated them away are no longer in your fixed point sister subalgebra. So that's the Albert's magic. And then from these constructions, he could formulate some calculus of these projections in the sister algebra, and we could get these identities. Okay, in particular, we could have this beautiful result that that as generators of your K groups, you can take the associated line bundles, like in the classical case. And then to speak intelligently about this ring structure, you need this idea of K0 group being a module of a representation ring. And this goes via KK bias. Anyway, so I think I stopped recording.
Ask a question? Can I ask another question? Sorry, like it's too exciting. Can you explain in a sentence or so, like what the groupoid representation of your C-star algebras, why does this lead to the multiplicative structure on the K theories?
No, this is not what leads to multiplicative structure. It leads to some identities in K theory that replace the multiplicative structure. The multiplicative structure we get from this module structure over the representation ring. But in general, it's very tough because you see, in classical topology, it works beautifully because you know that absolutely every vector bundle is associated to a compact principal bundle. You have such a theorem. You always have it. The frame bundle of orthonormal or orthogonal frames, okay, and orthonormal frames, and so you have it, and then you can fill out the whole K0 group by the action of different representation rings, because you might need principal bundles with, of course, with different structure groups. Okay, so it will be some kind of an inverse limit construction or something of a sort to get the whole K0 group. But some situations are simple, and in particular, when you look at CPN, the K theory of CPN is completely handled by just one bundle, the Hopf vibration. So you need just the representation ring of one group U1 with Laurent polynomials. And this action remains also, we have it also in the non-commutative setting, because these guys are bimodules. Yeah, so we can write generators as bimodules, and then we can sort of do everything consistently, make sure that the K0 relation is not violated, and we can reintroduce the multiplicative structure in K0, but by a lot of additional stuff. We have to talk compact quantum principal bundle, representation rings. That's the story for the next talk in January. Okay, yes. I stop recording. I stop sharing to begin with, and now I stop recording. Okay.